Welcome to Math with Professor V. This is video lecture for section 7.1 for business calculus on antiderivatives. So first, what is an antiderivative? Well, if you had to guess, I think you'd probably guess correctly. It's some function whose derivative we take to end up with a given function. And more formally put, if capital F prime of x is equal to lowercase f of x, then we say capital F of x is an antiderivative of f of x. So basically you take the derivative of capital F and you get lowercase f. So just to put some sense to all of these definitions, let's just work on an example. Find an antiderivative of the function f of x equals 2x. So this time you're going to think backwards because we're finding an antiderivative. So think to yourself, whose derivative did I take to end up with 2x? So just take a second, think about it, shout your guess or type it in the comment box. Okay, and remember, we're going to call this antiderivative for now capital F of x. Capital F of x could be x squared, right? Think about it. When you take the derivative of x squared, you bring the exponent, that 2, down front. You subtract 1 and your new exponent is now a 1, so you would have 2x to the first. Capital F prime of x would be 2x, which is what was given as lowercase f of x. But that's not the only possible answer or the only possible antiderivative. Let me ask you this. Could capital F of x also be x squared plus 2? If you took the derivative of this function here, you would get 2x plus, and then the derivative of any constant is 0. So again, you would end up with f prime of x equals 2x, which is f of x. So that also works. In fact, there's infinitely many options, right? Because another possibility would be, give me a number, x squared minus, we could do 1,000, pi, 42, whatever. So basically, we have a family of functions, right, that all are an antiderivative for f of x equaling 2x. The key component, or the identifying factor in this family of functions, is that they need to have that x squared term for sure, right? That way you end up with 2x when you take the derivative. And then what we write is we just say plus c, where c is some constant. And you could still have c be a negative constant. We just write plus c at the end. And this accounts for the infinitely many options that you could create here. Okay, good. So first we're going to focus on the indefinite integral. And basically it tells us, or it signals us, hey, find the antiderivative of this given function. So again, using the same definition, if capital F prime of x equals lowercase f of x, then here's kind of like your clue, go find the antiderivative, people. You have this integral sign right here, which looks like a long skinny s, not by accident. This is an integral sign. And then the function whose antiderivative you're finding goes right here. In this case, lowercase f of x, which we call the integrand. Okay? And then you always need this differential right here, dx, to tell you what variable you're finding the antiderivative with respect to. In this case, we're just working with a function of x, so we're going to integrate with respect to x. And then here's our antiderivative plus c. So for example, using this notation for the previous example, here's the difference. Instead of having to sit there and write out, find an antiderivative, all you have to do is write this symbol, the integral sign. You put the function whose antiderivative you want right here. Just don't forget the dx, and then boom. Okay, and it's not by chance, it's called antiderivative. We're undoing differentiation, exactly. So you know when you're asked to find a derivative, some things that signal that it's time to take a derivative is we write d dx, or we would write y prime, or f prime, etc. So now if you want to go the other way, you write an integral sign, okay? All right, good. So how do we go about taking antiderivatives? Literally undoing the differentiation process. So we got to go backwards. So here's the power rule that we use just so long as n does not equal -1. It doesn't work for that case. We'll talk about it in a hot second. Don't stress. So for any real number, n not equaling -1, the integral or antiderivative of x to the n dx equals x to the n plus 1 divided by n plus 1 plus c. So here's how I say this rule out loud to myself or to my students. You add 1 to the exponent when you're finding an antiderivative, and then you divide by the new exponent. So I want you to pay attention right here. You have x to the n, so when you take an antiderivative, you add 1 to that exponent. Now it becomes n plus 1, and then you divide by the new exponent. And that's undoing the differentiation process, right? Think about it. When we took the derivative of x to the n, what did we do? We multiplied by the exponent, and then we subtracted 1 to get the new exponent. So we're undoing both of those operations. Instead of multiplying, we're dividing, and instead of subtracting 1, we're adding 1. Okay? You probably could have figured out the rule on your own, huh? You don't need me. And then similar to differentiation, like if you have a constant times a function, right? You can just pull the constant outside the integral sign and find the antiderivative of the function. And then just that constant comes along for the ride, okay? You can also distribute the integral sign across a sum or difference of functions here, okay? And that's pretty much all we're gonna talk about for now. So let's work on some examples, and then we'll look at more scenarios, how to find antiderivatives when the problems get a little spicier. Here we go. So find the integrals or find the antiderivatives. So we have integral of 3x minus 5 dx. So remember, this integral sign means antidifferentiate. Exactly. If you want to remind yourself, this is 3x to the first, right? Go for it. So what do? We add 1 to the exponent. And the 3, he's just going to come along for the ride. Remember, we just talked about you've got this constant, it's just chilling, okay? Hang tight, 3. So we're going to have 3. My new exponent, add 1 to the exponent, it's going to be x squared. And then I divide this by the new exponent. So whatever the new exponent is, you divide by it. Are we all right? Okay, very good. Minus... Now, here's just a plain old constant, 5. Whose derivative would you have to take in order to get 5? It's 5x, right? And if that's a little funky for you, think about it this way. Currently, when you have 5 all by its lonesome, like it is right here, oh, poor 5, so lonely, it's 5x to the 0, right? Because x to the 0 is just 1. So then when you add 1 to the exponent, divide by the new exponent, it becomes 5x. Also, just think to yourself, oh yeah, if I take derivative of 5x, 5. Boom. That's probably more comfortable for you. And then we're not done yet. No, we always have to put plus c when we're finding a general antiderivative or evaluating indefinite integrals like this. Okay, and that's it. Oh yeah, let's box that with pride and move on. But I don't want a wiggly box, you know, nobody wants that. Oh, there we go. Much better. Okay, example B, let's try another. We have integral of t to the 1/4 plus pi to the 1/4 dt. Notice there's always that differential here. So you have to have the integral sign, the integrand, the function whose antiderivative you're taking, and then dt in this case, since we have a function of t. It should make a little sandwich. Here's the breads, right? And this is all the filling. If you don't have this part, it's a no-no. So the math police will come snatch you quick. All right, add 1 to the exponent. That's going to be 1/4 plus 1 5/4. And then we divide by the new exponent. Plus, and then watch out, this one, it was meant to maybe trick you. Pi to the 1/4 is just a constant. It's just a constant. So think back, how did we find the antiderivative here of 5? We just added the variable of the function. We multiplied by it. So we're going to do the same thing here. This might as well be 5. It might as well be 5, I know. So this is pi to the 1/4 t times t plus c. And then just to clean it up, instead of having divided by 5 over 4, I'm going to write that as 4/5 exactly. T to the 5 over 4 plus pi to the 1/4 t plus c. Voila. Now, when you do enough of these and you get kind of slick, you might just go straight to here and already start flipping. Which is no big deal. That's really good. Okay. Now, remember exponential functions? We found their derivatives, which means we can go ahead and find their antiderivatives. So, antiderivative of e to the x dx is just e to the x plus c. That's no surprise, right? When we kept differentiating e to the x, we got back e to the x. So same thing when we find the antiderivative, just don't forget to put plus c. Now, if you have some little constant up in the exponent, when you find the antiderivative, you divide by the constant that's being multiplied by x. And let me show you an example. Basically, this is undoing the chain rule. And we're going to look at more general cases in the next lesson about how to undo the chain rule when we learn u substitution. But for now, just use this little slick trick because it'll save you time. So pretend, let's just say my function was e to the 3x. And I asked you to find the derivative, not antiderivative, derivative. Okay, so pretend this is like a week ago. F prime of x would be, well, derivative of e to the something is e to the something times the derivative of the something, times the derivative of the exponent, which would be 3. Yes? So it's 3e to the 3x. So now when we go backwards, when you take an antiderivative, say you took antiderivative of 3e to the 3x, don't forget that dx. What's the antiderivative of this function? It's e to the 3x. But what if this 3 wasn't there? And what if I just had e to the 3x dx? Well, in that case, then your antiderivative would need to have a 1/3 in front, e to the 3x plus c. You see? Because anytime you take the derivative of e raised to some constant times x, when you do the chain rule, you multiply by that constant. So if you don't see a constant in front and you're finding the antiderivative, then you have to divide by whatever is up there. All right? And then similarly, if you're finding the antiderivative and the base is a instead of e, then you divide by natural log of a. So basically, remember when we would find derivatives, we would multiply by natural log of a. Now we go the other way, we divide by it. And then if you have k, x, and the base is a, then you divide by all that, k and ln of a. Okay? And then last but not least, if you have the antiderivative of 1 over x, or x to the negative first, then it's natural log absolute value of x plus c. So remember, our power rule does not work here because the power rule tells us we add 1 to the exponent, divide by the new exponent. That would be problematic here. If you add 1 to the exponent, you get 0, and we can't divide by 0, it's undefined. So just put to memory, antiderivative of 1 over x dx is natural log, and you do have to remember to put these absolute value bars around the argument, around x right there, because natural log's domain is restricted, right? X has to be greater than 0, so we want to make sure we don't have anything undefined or any domain errors issues, okay? Good. It's not as bad as maybe it sounds. It's actually quite fun. So let's start working on some examples, okay? So you can have yourself a grand old time taking antiderivatives. Here we go. Antiderivative or integral of 15x rad x plus 2 rad x dx. So think back. Like if you had to differentiate this function, you wouldn't leave all those radicals in there, right? Wouldn't you rewrite them as rational exponents? Well, when we're finding antiderivatives, we do the exact same thing. So I'm going to rewrite this now as integral 15. This is x to the first and x to the 1/2. So when we simplify, we add those exponents. 1 plus 1/2 is 3/2. Plus, this is 2x to the 1/2. And then dx. Keep writing dx every step of the way until you actually find the antiderivative and put plus c. Okay, and then now we're ready to take the antiderivative. The constants just come along for the ride, pay them no mind. And then add 1 to the exponent. It's going to be x to the 5/2. And then divide by the new exponent. plus 2x to the, if we add 1 to 1/2, it's 3/2 divided by 3/2 plus c. Good. Okay, now we just have to call in the cleanup crew, but I want you to notice something. Dx is gone, right? I took the antiderivative and I put plus c. So integral sign and dx, they go away at the same time. Your sandwich dissolves at the same moment, okay? And then now let's see here. So this is going to be 15 divided by 5/2 is times 2/5, x to the 5/2 plus 2. And then the next term is going to be 2 times 2/3 x to the 3/2 plus c. So now we just got to simplify those constants. If it helps you, remember this 15 is over 1, so is this 2. And then the 5 and the 15 cancel, so this is just 3. 3 times 2 gives me 6, x to the 5/2 plus, nothing cancels here, so then that's just 4/3 x to the 3/2 plus c. And that's our antiderivative. Now, if you're nervous, if you did it correctly, which I would be if I was first learning how to find antiderivatives, you just check your own answer. How? You take the derivative of it. You go, okay, I would bring the exponent down front and multiply. So 6 times 5/2, 30 over 2, that's 15. Subtract 1 from the exponent, x to the 3/2, very good. And then keep going, 4/3 times 3/2, that's 2, boom. Subtract 1, x to the 1/2. So you can always check your work, which is nice, okay? You don't need to do math in the dark, unsure of your success. Here we go. Integral -4 e to the 0.2v dv. So I'm going to give you a hint. You need to use one of those properties up top for finding an indefinite integral of an exponential function. Use the one where it's e to the kx. So our variable here in this integral is v, not x, but it's okay. It's just a different letter. They're trying to keep it interesting. We appreciate the effort. So here we've got -4. Just pay it no attention. Constants come along for the ride. Antiderivative of e to the something is e to the something. And then k in this case, k is 0.2. So I'm going to divide by that here when I take the antiderivative. And then we have plus c. Now that's messy, don't leave it like that. So 0.2, right, that's 2 over 10, 1/5. -4 divided by 1/5 is the same as -4 times 5. So this is -20 e to the 0.2v plus c. Boom, there's our antiderivative. Again, are you a little nervous? Maybe, that's okay. So let's just check together. So I'm going to take the derivative with respect to v of what I'm thinking the antiderivative is. I just want to make sure. Actually, let me put the plus c in there too, just so we can be thorough. Okay, when we take the derivative and you have that constant, it just comes along for the ride. Derivative of e to the something is e to the something. And then by the chain rule, I have to multiply by the derivative of 0.2v, which is 0.2, plus the derivative of c is just 0. And then lo and behold, yes, -20 times 0.2, that's going to give me -4 e to the 0.2v. Boom, we're so good. All right, couple more. We have integral of 2y minus 1 quantity squared dy. Okay, so until we learn the next lesson that covers u substitution, so basically how to find the antiderivative when you have composition of functions, we right now just have to expand all of this. So we're going to multiply out 2y minus 1 squared. You can write it twice and FOIL, or hopefully you know the shortcut. If you multiply this out, it's going to be 4y squared. Don't forget the middle term, minus 4y plus 1 dy. Is there a rule for that? Yeah, you square the first term. You take these two guys, multiply them by each other, and double it, and then you square the last term. That's why it's always positive. And then now just go term by term, finding the antiderivative of each guy. So antiderivative of 4y squared. So you add 1 to the exponent. on the variable, divide by the new exponent. The 4 just comes along for the ride. Minus, now this is 4y to the first. So you just leave that first 4 there. Add 1 to the exponent, divide by the new exponent. Plus, when you have a constant and you're taking the antiderivative, you just slap the variable of the function on it. So this is all y's, right? We have a function of y. So antiderivative of 1 is 1y, just y, plus c. And then clean it up because 4 over 2 reduces. Personally, I don't like when it looks like this. It's not wrong, but I usually prefer to write it with the coefficient all by itself out front like that. 4/3 y cubed minus 2y squared plus y. You have to put plus c though, otherwise it is not correct, your antiderivative, okay? Again, the math police, they will come for you. Oh yeah. Okay, here's one more. Do you want to try it on your own? Don't say no. Here, I'll give you a hint. You're gonna write each of the terms in the numerator separately over the denominator and then simplify. Come on, pause the video, try it. Okay, did you do it? I hope you did. So this is gonna be integral 1 over cube root of z minus 2 cube root of z over cube root of z dz. Boom. Then what is this going to be? Don't take the antiderivative yet. So notice, I'm just cleaning things up. I still have my integral sign. I still have my dz. 1 over cube root of z, I want to put it in integral friendly format, just like we would rewrite things in derivative friendly format. Let's write that as z to the negative 1/3 power, because this is z to the 1/3 in the denominator. And then look, oh, this is fabulous. These just cancel out. Minus 2. I love it. I love it so much. Keep that dz. Look, here's my integral sandwich. Boom. Okay, now we're ready to find the antiderivative. So you're going to add 1 to the exponent, divide by the new exponent. So it's going to be z to the 2/3 divided by 2/3 minus antiderivative of a constant. Just slap the variable of the problem on it. So minus 2z plus c. You might notice now is a very lovely time to start crossing your z's in math. Otherwise, they look a little too much like 2's, right? Yes, yes. Okay, and then final answer, just simplify. This is going to be 3/2 z to the 2/3 minus 2z plus c. Good job. Okay, let's look at a little bit of econ applications. Okay, and remember marginal cost. Marginal cost function is the derivative of our cost function. So now that we know antiderivatives, we can go backwards and find cost functions. So that's precisely what we're being asked to do here. It says find the cost function for each marginal cost function. So remember, marginal cost is c prime of x, and the cost function is c of x. So now they're going to give us this guy, and we have to find the OG, the original cost function. Okay? First one, c prime of x is 0.2x squared plus 5x, and then they also told me the fixed cost is $10. So remember, fixed cost is the cost that is incurred even when you make 0 products, 0 items. So basically the cost, that's supposed to be a C, but you can't even tell. The cost of making 0 items is $10. That's my fixed cost. That's what that's telling me. Or basically 0, 10 is x, C of x. Why did they tell me that? Because at the very end of the problem, they want me to not leave it with a plus C in my answer. I'm going to actually go and find what that C is. Okay? So here we go. They gave me C prime, I need C of x. So they want me to find C of x. That's going to be integral of C prime of x. What am I forgetting? The other bread, dx, yes? Integral dx. Those are your breads. Here's the middle part. Okay. Integral, what was C prime of x? 0.2x squared plus 5x. Don't forget the dx. Okay. Add 1 to the exponent and divide by the new exponent. So this is going to be 0.2x cubed divided by 3 plus 5x squared divided by 2 plus some c. Okay, this is c of x. Now, my job is to find this c. So how do I do it? I do it by plugging in 0 for x and replacing c of x with 10. So c of x is 10. That equals 0.2 times 0 cubed over 3. I mean, these are all just going to be 0, but I'm being so thorough right now. Good? Okay. So that means 10 equals 0 plus c. So c is 10. So now I can say, all right, c of x. I got like way too excited and wrote way too big. Okay, c of x is 0.2 x cubed divided by 3 plus 5/2 x squared plus, now I know c is 10. Okay, and then 0.2 divided by 3, let's just write that as 1/15 x cubed plus 5/2 x squared plus 10. That's our final cleaned up, ready for business cost function. How was that? Okay, good. I have 2 more little relaxing examples for you. These are not so bad, huh? So now they're telling me marginal cost function c prime of x is x plus 1 over x squared, and this time 2 units cost $5.50. So that means the cost of making 2 units, if x is 2, is $5.50 or 5.5. So you have 2 comma 5.5 as x, c of x. But that's still going to help us find c. It's just going to be a little more work. It won't be as fun as plugging in 0, sadly. Okay. So c prime of x, the marginal cost function, is x plus, instead of thinking of it as 1 over x squared, that's the same as x to the negative second, right? I'm trying to get it ready so we can take an antiderivative. And then c of x is going to be integral of x plus x to the negative second dx. So here we go. This is x to the first, add 1 to the exponent, divide by the new exponent. You'll have x squared over 2. I like writing it as 1/2 x squared much better. And then add 1 to the exponent, divide by the new exponent. It's going to be -1, right? And then we're going to divide by -1. And then plus c. Okay, just clean that up. So c of x is 1/2 x squared minus, because I can just replace, instead of writing plus with this negative down here, just write it as minus x to the negative first. That's 1 over x plus c. Now we got to come through and find this c, and I do that by substituting in 2 for x and setting this c of x equal to 5.5. Okay, so then we have 5.5 equals 1/2, remember I'm plugging in 2 for x this time, minus 1 over x is 2 plus c. And that's all equal to 5.5. Okay, so then we're going to have 2 squared, that's 4, times 1/2 is 2. So 5.5 equals 2 minus 1/2 plus c. 2 minus 1/2, 4 halves minus 1/2, that's 3 halves. 3 halves is 1.5, 1.5, so c is 4. Okay, that's it. So let's put it all together. C of x, this guy, right? 4. C of x is going to be 1/2 x squared minus 1 over x plus 4. Lovely, fabulous. Okay, last one. You ready? Okay, find the demand function for the marginal revenue function. Recall that if no items are sold, the revenue is 0. So that tells me when you have your revenue function r of x, right? That's revenue. They're telling me r of 0 is 0. Okay, so let's see, what did they give me? They gave me marginal revenue, so r prime of x. I could find the revenue function if I take the antiderivative, but wait a minute, they want the demand function. They didn't ask for the revenue function. How am I going to get there? Well, remember revenue, R of X, is P times X, and P is our demand function, the price. So our demand function would be revenue, R of X, divided by X. There's our demand function. Okay, so we can get there. We just have one extra step, basically. We're going to find the antiderivative, so we get the revenue function. And then to get the demand function, I'm going to go ahead and divide that revenue function by X. And then we're done. Okay, just one extra little step. So here we go. Let's get started. So R of X is going to equal antiderivative integral of 50 minus 5x to the 2/3. What is missing? Hopefully it bothers you. Like it bothers my eyeballs, right? Oh no, there's that dx. Good. Antiderivative time. So 50 is just a constant. Antiderivative, slap an x on it, minus. Now we're going to add 1 to the exponent, divide by the new exponent. And the 5 just comes along for the ride. So we have 5x to the 5/3 divided by 5/3 plus c. So we can clean up. R of x is 50x minus 5 divided by 5/3 is the same as 5 times 3 over 5. So those 5's cancel, and then you're just going to have 3x to the 5/3 plus c. Now, don't divide everybody by x just yet. Remember, they told me when no items are sold, the revenue is 0. So this is to help me find c. And hopefully it's pretty clear. C is just going to be 0, but we could go through the steps of writing it out. So R of 0 would be 50 times 0 minus 3 times 0 plus c, which is 0. So c is 0. Okay, so here's my revenue function. 50x minus 3x to the 5/3. And I don't have to put plus c anymore. I know it's 0. So if I want the demand function, P, it's equal to R of x divided by x. So I'm going to take 50x minus 3x to the 5/3 and divide by x. So you can split each of those terms over x. Ooh. Minus 3x to the 5/3 over x, like that. And then for our final answer, see these cancel. So then you'll just have 50 minus 3, this is x to the first, so 5/3 minus 1, that'll be x to the 2/3. Boom. Okay, so that concludes the lesson. Hope you found it helpful. Don't forget to give the video a thumbs up, subscribe if you haven't already. You can also follow me on Instagram and TikTok, Math with Professor V, see what sort of shenanigans I'm up to. And to make sure that the math police stay away, you can shop my merch. Anyways, that's it. Coming up soon is integration by U substitution, finding antiderivatives, and we need like one other technique to help us evaluate or do more integrals. Okay, coming soon. I'll be back sooner than later, guys. Bye.